Hello everybody, welcome to video 3 and we'll get started real quick. Let me jump to the share screen. Share screen, not to the lecture notes, but I'll go right here. So what we did the last two videos was we went through the ANOVA model basics, just really laying out the basic ANOVA model, which again, if you guys recall with the Ken data, we set up the basic model as looking, I'll type this just basically in English. So we had our H0, if we use the Ken data set as the example, where we had the four designs, the four designs of the packaging. And we were looking basically at this now, whether or not the four means, the on average sales for the four designs were equal. So we dissected that. And like I said to you before, this takes where you guys at 513, takes where you guys ended at 512 and basically blows it up so that you guys can see, a little bit more of what's going on behind the scenes. From there, we talked about power, and you got a little exposed to power in 506. The end of 506, probably laid it out for the t-test, possibly the independent sample t-test. But again, remember, the power we're looking for the ANOVA model is power to correctly reject that false null. That at least one of the groups is significantly separating from the others. Now we're getting into chapter 17. And what we want to start talking about in the model is some of the mathematics behind confidence intervals. So basically getting our on average 95 or 90% or 97.5% confidence intervals for the respective means. And we're going to see it also for the mean differences between any pair, any combination of pairs we want to focus on. From there, we're going to talk about contrast. So this is going to go beyond looking at just two means and possibly looking at collection means. Then from there, or I guess intermixed in there, we're going to talk about multiple comparisons. So when we start looking at, the alpha level of the model is set for this null. But when we start dissecting things with confidence intervals, comparisons, or what we call contrast, there's an alpha associated with each of those. And we want to talk about, well, how do you account for what we call in this situation a multiple comparison? We'll just give a little flavor introduction of that in video 3, but we'll dissect it more in video 4, the second part of chapter 17, as well as talk about power of the contrast. So that's what we have to do tonight. And as we get to this, we're going to jump to our PowerPoint slides. So the slides for chapter 17 that you guys can see. I call this chapter 17 as the slides that you guys will find on D2L. So our cell mean model layout we saw last two videos for the ANOVA model. Again, a little different than the regression model you guys were exposed to in 512. But our main inference, our main focus is trying to figure out the best estimate of the cell mean, counting for the individual errors and going from there. And again, when we talk about the ANOVA model, analysis of variance, remember we said the definition of analysis of variance really goes at looking at the variability of the estimated cell means across the levels. So for the Ken data, it was the 4 levels of design. And we said, well, we need a reference. And so the analysis of variance model looks at the variance between the cell means compared to the pooled or average variance of the observations within cells. That pooled variance within is estimated by the MSE. And we saw that the last two videos. So now, we focused last week on interpreting the cell means. And now what we want to do is figure out ways to look at, okay, we saw how groups separated last week. Well, can we even take that a little further? And we gave a little introduction of it based on the video last time, but can we do it even a little bit more? And we're going to do this through the process called estimation and contrast. And basically, we're testing levels of the factor variable, the variable in the class statement, such as designed for the Kenton data, and combinations of that. So again, we'll see that a little bit more tonight. Here's an example from a depression trial. So you guys are going to see me talk about a lot of these trials throughout the course. We talked about the cocaine addiction treatment study. This one was focused on, it was centered at the University of Washington and focused on treating people suffering from clinical depression. This group right here illustrates the group at, the group of people who came into the study suffering from high severe depression. We call this high severity group. And they were given one of 4 treatments. And we looked at their performance over the 8 weeks. The 4 treatments in purple is placebo. The green one is medication, some form of antidepressant. So with the placebo and the antidepressant, the packaging of the antidepressant and the placebo looked exactly the same. So the patients were blinded. They did not know whether they were receiving an active medication, active antidepressant, or they were receiving the placebo. So the placebo is kind of our control group, our comparison group. The blue and the red are 2 forms of psychotherapy, 2 forms of counseling. Cognitive therapy, where again, the person becomes aware of their depressive symptoms. Maybe they're depressive stimulators that get them into depressive mood. So, cognitive behavioral therapy, the cognitive an understanding of their depression. The red is called behavioral activation. And this is to try to get the people to activate behavioral changes once they have these depressive onsets happening. The outcome you see on the y-axis is the Beck Depression Index. One of the things with a lot of psychological scales, psychological studies, they have these scales that quantify whatever kind of measurement they're trying to quantify. In this case, we're trying to quantify depression, how depressed an individual is. Aaron Beck, you guys may be aware of Aaron Beck, the name. He's one of the pioneers in depressive research. He has an institute on City Line Avenue called the Beck Institute right here in Philadelphia. So he's, he's been really one of the pioneer researchers in treating depression, treating anxiety. He came up with this questionnaire called the Beck Depression Inventory. I think it has 63 items. And basically, it's asking people how they feel. And like any kind of questionnaire you guys have been exposed to, the response an individual gives is kind of on that Likert scale. In this case, I think the scale is 1 to 5, or my fault, 0 to 5 or 1 to 6. And the Beck Depression score is the sum of the respective items over the scale. One of the things that the researchers do a lot is they create items that have what we call reverse scoring, which basically questions asked in the opposite direction. A lot of this is to make sure that the people are paying attention to the questions and instead just filling straight down a column or whatever. So we'd be able to flag when a person's answer is not consistent with his or her other answers. And in that case, I can kind of flag when a person's not taking the scale seriously. So really the individual reliability of that scale is in question. So let's just get a lot of the real assessments from the fake assessments. With the Beck Depression Index, the lower the score, the better the individual is. The higher the score, the more impaired the person is with depression. So now, when we start looking at this, at 8 weeks, which ended up being the treatment period, including the placebo group, this is the overall p-value for the overall ANOVA. So based on the available data, we have sufficient evidence to indicate that on average, the 4 groups are not the same at week 8, with at least one of them separating from the others. When we look at this visual, it appears that cognitive therapy and placebo on average are the worst, whereas medication and behavioral activation on average are the best. So it appears to be, what's really driving this overall ANOVA effect is the green and the red being significantly lower than the other 2. Again, we're just eyeballing this. We will test this subsequently. So we see that right now. Now this was a huge story at the time. This was the 3rd trial to examine psychotherapy compared to medication in the treatment of depression. This was the 2nd trial that involved cognitive therapy as a treatment approach for people suffering from depression. In this study, in the previous study that had cognitive therapy, the interesting thing was cognitive therapy was effective in the treatment of depression. In this follow-up study, we see it's not cognitive therapy, it's behavioral activation that on average performs almost equal, slightly less compared to medication. So this was big story, big news. So it's kind of like the stability of the cognitive therapy effect we don't see compared to the earlier trials. Whereas this new trial, this new psychotherapy, behavioral activation, is stepping out as a possible treatment approach. So that created a lot of questions as we started moving on. And again, with any kind of randomized clinical trial, as you guys see with any kind of medications to treat some kind of issues, whether, you're talking about, the SARS outbreak in the, around 2008, 2010, or you're talking about the coronavirus outbreak, the 2019, 2020 issues. One of the things with randomized clinical trials is we try to show reproducibility of an effect. Here, cognitive therapy is not showing the reproducibility of the effect, but behavior activation is showing a first, quote, successful effect. Again, requiring reproducibility of the BA effect. Again, a lot of times you see the abbreviations used as commentary. So again, what we see driving that overall effect, we see placebo and cognitive therapy seem to be performing on average worse than BA and medication. It appears placebo and CT are no different. That's what we see. Again, we can't really quantify no difference unless we go through that bioequivalence topic we did last week. But it appears CT is inferior to medication. CT is inferior to BA. Again, that's because CT is a lot higher than those 2. Placebo is inferior to BA, and placebo's inferior to medication. Again, it's the purple being a lot higher than the green and the red. That's what we get from eyeballing it. But can we statistically say this? Can we statistically say that placebo is statistically inferior to BA medication? And can we say CT is statistically inferior to medication behavioral activation? So the question is, can we say this statistically? And the answer is yes. And the one way we're going to do this is forming what we call a contrast. Now, contrast, you were exposed to it in a sense in 512, but not specifically by the name contrast, How we do this in SAS and true in R and STA and SPSS is we form what we call a contrast and estimate statement. So we need to form these statements. And again, the R syntax runs a lot similar to SAS, the STA syntax as well. SPSS run similar, but they use this thing called a test statement. Again, we're going to expose it in SAS. Again, if you guys want to see the R, the STA, the SPSS, a quick Google, YouTube of contrast estimate will give you a lot of examples of the basic formations. So we can, as we said, do this through a contrast and an estimate statement in SAS. One thing we're going to see with the difference between the contrast and the estimate statement, the test statistic used in that statement is a T, so a T distribution, whereas the contrast uses the F. And, you know, we'll give a little bit more exposure to that. One thing we have to think about, though, is when we start doing these different comparisons, we're doing what we call a lot of contrast. So one thing we need to keep in mind is how many of these are we doing? Now with each contrast has an alpha level associated with it. Because in essence, we're going to form a null for each contrast. That will have a null, that will have an alternative. Each null has an alpha. So when we start doing a bunch of tests, one of the issues becomes is, okay, well, we have a type 1 error possibility for each test we do. And as we do multiple tests, does our type 1 error stay the same, or does it start to increase or decrease? So we start getting into this issue of multiple comparisons. And how are we going to handle the multiple comparisons? The multiple comparisons is kind of like having, if any of you guys play darts or shoot baskets, and what I think a lot of times in the multiple comparisons, it's like having darts and just throwing blindly at a dartboard. Or if you're playing basketball, throwing blindly at a basketball hoop. Not concentrating, but just throwing in the direction. A type 1 error is falsely rejecting a true null. With each null hypothesis, we have that possibility. And the alpha level is kind of like when you're blindly shooting at a dartboard or a basketball, that you either hit the bullseye or hit or make a basket. You have no intention of doing that, but just by blindly going in that direction, you do that. You know, it hits the bullseye if it's a dartboard. The basketball goes in the hoop if you're shooting basketballs. That's just, you know, in essence, blind luck. That's a type 1 error. So as we start doing these multiple comparisons, are we going to accidentally make a type 1 error just by accident? And again, you know, an alpha 0.05, that, you know, in essence, that says, well, you know, 1 out of 20 chance you make a type 1 error. So, you know, if you're doing a lot of them, you know, it's that what you were exposed to in 5 or 6, the law of large numbers. Well, if you do it repetitively, chances are you hit a type 1 error by accident go up. Well, this idea of multiple comparison, and we're going to dissect it more in the next video, but I just want to give you a little introduction to the topic as we start getting into this contrast and estimate issue, is that, okay, well, according to Savage and Olson, this American Journal of Epidemiology, so with statistics, we're going to see there's a lot of overlapping areas involved in statistics. One of the things I'm involved in is dealing with data with psychological studies. So sometimes that area of psychological data analysis, sometimes referred to as psychometrics, it's not entirely analytical approaches for psychological data, but a lot of times people use psychometrics as a term for analyzing psychological data. For studies involved in, biological studies, sometimes you guys will hear the term biometrics. But in areas of sociology, like education research, income research, the area of clinical trials called epidemiology, data dealing with, politics and all that. Statistics branches way out and covers a lot of areas. Well, with a lot of the epidemiological studies, this issue of multiple comparisons came up. And what Savitz and Olshan said, hey, if you're doing a bunch of different associations, a bunch of contrast, a bunch of estimates, well, if you have n independent associations are examined for statistical estimates, probably making at least one of them to be found statistically significant is given by this formula. 1 minus the alpha level, all raised to the nth power. Well, what does that mean? Well, let me jump you guys to SAS real quick. I'm going to jump to the, let me just clear this. I'm going to go real quick here. So let's make a real quick data set. N equal 1 to 25. So just basic, call this type 1. So this is 1 minus, set the alpha level to 0.05. So I got the formula right there that the formula we got right there from the Savitz-Olshan. So again, if you guys see 1 minus alpha to the n. So that's the formula we have. I'll output this. I'll end. I'll run. And let's go ahead and take a look at, I can type, look at the output real quick. So here we go. Again, it's just a formula. So for an alpha level of 0.05, here we go. So now this is showing the probability of a type 1 error as you do multiple independent tests, multiple independent test of association. Well, if we have one test, our type 1 error is 0.05. That makes sense. But look as you start doing multiple and multiple tests. If you do 5 tests, 5 quote contrast, if you will, the probability of making a type 1 error then, and that means a type 1 error in at least one of them, in at least one of the tests, is more than 1 out of 5. Now it's 22.6%. If you have 10 tests, the probability of making at least one type 1 error is slightly more than 2 out of 5, 40%. So no longer 1 out of 20. No, we're at 2 out of 5. If you're doing 14 tests for whatever reason, if you think about this, 14 tests, when would you make 14 tests? Suppose the factor level, in this case here, has 6 levels. Now, the Kenton data had 4 levels. Now, for 4 design packages of the serial. Suppose you have something that has 6 levels. Well, if we want to make all the pairwise comparisons, that means for the 6 levels, we're choosing 2 at a time. Right, so go back to your 504, 505 counting techniques. 6, choose 2. Okay, 6, choose 2. Right, so we know, okay, that's 6 factorial, right, over 6 minus 2 factorial over 2 factorial. So that becomes 6 times 5 over 2. That's 15. Right, so if we have 6 levels, the probability of at least one of them, if we go right to 15, at least one of them of making a type 1 error in at least one of them is 53.7%. That's more than 1 out of 2. So this multiple comparison issue really becomes a big concern. And then look, if we jump all the way to 25, it's almost a 3 out of 4 chance we're making a type 1 error. So this Savitz and Ocean formula, wow, as you start doing multiple comparisons, the probability of making at least one type 1 error really skyrockets. That really goes up. So this is something we need to really worry about as we start moving forward. So that little equation really shows that the type 1 error here can really take off. So we need to keep this in the back of our mind, something we need to address. And you had a little exposure to it in the end of 512. When you guys started doing the one-way ANOVA, and you did something called a Tukey adjustment. We're going to talk about that, we're going to talk about that momentarily. Now, if you guys start looking at, so we need to keep that in mind. So this issue could be a pothole. And again, I know some of the, some of you may be familiar, may not be familiar with some of the terminology, but a pothole, when you're driving, it's one of those holes in the road that, your car tire hits it and creates a whole bunch of damage in your car. We don't want to hit a pothole as we start doing the data analysis. So we need to keep this formula in mind. This is something we need to keep in mind. But there's also something else we need to keep in mind. And that's this Savitz and Ocean idea of N independent associations. So our further discussion on multiple comparisons needs to focus on this idea versus this formula. There becomes an integration of the two that we need to account for. We're going to talk about 3 approaches that kind of integrate them together. But now, if we go back to the Kenton data, and with the Kenton data, we saw the on average cases sold for the 4 designs had these means and these standard deviations. And then remember, the standard errors, ends up being the root MSE over the square root of the sample size. So again, visually, we can look at the cases sold as looking like this, And so sort of what we did last video, where we start looking at the comparisons, we did it 2 ways. The one way is we used proc format and SAS to make the reference cell whichever group we wanted to compare to the other. And the second way we did is we used the LS mean statement. So the least squares mean, and we made the PDIF option in SAS, which correspond to pairwise differences. So we did that. Now this is a visual, just like we did with the depression study data, of the cell means. Now, let's take a look at another example. And in this other example, I want to bring in to you guys confidence interval formulas. We saw them before, but we want to bring them in again. So, so in this setup, we're going to do chapter 17 in kind of 3 approaches. So if I go back to the word, so the 3 approaches are really looking at the idea of comparison of the cell means. And we're going to do it through the confidence interval approach, a formal contrast. We already kind of gave this layout of the intro to multiple comparisons. But in this case here, we want to do it both quantified and graphical. So I want to highlight that issue to you guys as well. So now we go real quick here. Let me jump real quick. I want to get back to the textbook. So we go to the textbook. Let's go to chapter 17. Make this a little bigger. So the example we're looking at now is page 735. So in this case, in this study, this data on chapter, chapter 17, page 735, we're looking at 4 different rust inhibitors. They're coded brand A, brand B, brand C, brand D. So obviously, we don't know what their exact name is. We're just giving them these categorical labels. So in this situation here, we get 40 pieces of metal or whatever that we're going to call the unit, right? So the unit is where we're getting the data from. So for each of these, we randomly assign one of the 4 brands. So each brand's getting exposed to 10 units. And then for each of these, we give a grading of, how, in essence, protective the coating is for the piece of metal being protected against rusting. So in this case, the higher the score, the more effective the rust inhibitor from preventing the piece of metal of rusting. So now we want to compare our 4 brands against, in this case here, with an alpha of 0.05. Here's the data here. Here's the data here. The overall mean of the 4 brands, as you guys see, is 60.25. The cell means are right here. So visually, we can see that brand B it appears superior to the other 3. It appears like it's statistically separating from the other 3. Now, again, we have to do the analysis to test this, but just from a visual, it appears this is separating from the other 3. Kind of like the Kent data, C is the next one. Now it looks like A and B are basically, pretty, comparable with respect to inhibiting against rust. And it appears like the 3, the A and D are kind of like our design 1 and design 2 of the Kent data are the worst. So in this case here, we have this data here. So let's go ahead and take a look at it in SAS. So I'm going to pull up the SAS code. So again, this was an illustration of our alpha level. Right, so in this case here, I'll call this chapter multiple comparison basics. But let me go ahead and pick up the chapter 17, 735. So we have the data here. So I'm going to put the number line on again. And if you guys remember, in this white box here, I type num on, and this gives me the number lines down the side, which, obviously for teaching, lets me tell you guys what I want to do. Line 7, this sets up how SAS looks in the SAS listing file. Most of you guys are using the HTML output of SAS, which is totally fine. Sometimes for me, when I'm running a bunch of analyses, the HTML window that opens really slows down SAS. So if I use the tools, options, preferences, let me just hit that one more time. If I go to tools, options, preferences, if I click on this, I go to results. Sometimes I'll turn off the HTML and the graphics. And that's just because a lot of the output just really slows up SAS, and especially if I'm doing a bunch of iterative complex analyses. When that's turned off, the output you guys see goes to the output generated by SAS goes to this SAS output window. This is sometimes called a listing window. And with the listing window, SAS looks like this, and all this print that you guys hear is sometimes called SAS monospace. But it's not as space absorbing, time consuming as the HTML output. So when you guys look at this line 7, this is me telling SAS how I want that SAS listing to look like. And the LS equal 90, PS equal 50, it's line size, page size for the options. That has the SAS output fit very nicely in the typical 8.5 by 11 piece of paper. The form delim equals apostrophe, space, apostrophe. In the listing file, that tells SAS to skip a line rather than a page for every proc freak output. I mean, any kind of proc output. So I'll use, most of my programs will have this default line. If you're using strictly the HTML, you don't need to worry about that line. If you turn the HTML off, this makes the SAS listing look, for lack of a better word, normal. And instead of jumping a page for every proc producing output, it just skips a line, which is a little bit more space consuming. But if we go back to the Rust inhibitor data, I'm going to create this data Rust, which has the 40 data values. So in this case here, the Y is rating, that's the outcome, the grade on the Rust inhibitor. The brand is the factor variable, and then the unit is the number of, the observation, the data point within each level. So you can kind of think of the brand and unit as basically the IJ subscript in the CellMe model. So let me go ahead and load the data. So here's my data. Right, so as you guys see, it's 40 observations, 3 variables. If I go real quick, I'll print it out. So that creates my printout. So there's the 40 data values. From here, I could use line 60 to 61. And again, if I want to send the data set to a RTF file, which is a rich text field, which opens up in Word, I can use this ODS command, which you guys were exposed to in 5.11. So ODS, I'm creating an RTF file, and the RTF file is going to be in my C drive called example.rtf. And then when I want to close any SAS output going to this RTF file, I just type that ODS RTF close. So anytime you have this starting, anything that produces output goes to that file until I hit the close. So this one here is giving me basic descriptives. Basic proc means where I'm going to show the n, the mean, the standard deviation, the confidence limits for the mean, and this is going to make the output at most 2 decimals. The class statement for our categorical predictor, and then var is the Y variable. When I do this, this is giving me, like I said, for each level of the brain, the number of observations, right? The n, the number of data points, the number of observations, the number of rows of data where brand is. N is counting number of non-missing values, which we don't have any missing values in this. But here are the cell means we saw on the graph. The standard deviations and the confidence limits. Now, pay pretty close attention to this one, frame 1. So we're 95% confident, based on this descriptives, that the true average rating for brand 1 lies between 40.99 and 45.29. So let me go back here to, to Word. And let's go ahead and go brand 1. So we got this confidence interval, as we just saw in our data set. 40.99 is the lower bound, and 45.29 is the upper bound. All right, so we just go right there. And so if you guys are looking, the width of that confidence interval is 4.3. And let me just do one more in this, just to summarize as we're going back and forth. My fault. So we go here, let's take a look at brand 2 while we're here. So brand 2, if we start looking at this guy and go, okay, so its lower bound is 87.85. The upper bound is 91.03. So based on available data, we're 95% confident that the true average rating for brand 2 lies between 87.85 and 91.03. So let's just go ahead and write that down. So we got brand 2, its lower bound is 87.85, its upper bound is 91.03, and this gives us a width equal to 3.18 if we're doing the math real quick. All right, so we got that right there from our Rust data. All right, so we'll call this chapter 17, page 735. All right, so we got that right there. Just what we just laid out real quick there. So that's all cool. That's all cool. And again, we get the same thing for brand 3, brand 4. Again, we could see visually. So brand 3, it's the middle of the pack, has the smallest standard deviation. Brand 1, which is, I'll call it the third best, has the biggest standard deviation. All right, so we just see this visually. So we haven't ran the ANOVA model yet. We're just descriptively summarizing the data. Well, when I start looking at this, when I'm going to fit the ANOVA model, I'm thinking, I'm going to reject that null, that the means aren't equal with at least one separating. So I'm thinking here, that group brand 2 on average is going to be statistically superior to the other 3. When I look at the standard deviations, now the smallest is 2.17, the biggest is 3. I get 10 per cell. I don't think there's going to be enough evidence to reject that null for the equality of variance. And so I'm thinking, we don't have sufficient evidence to reject that null of the equal variance across the 4 cells. So that's just me looking at the data, making that assessment. We haven't statistically analyzed anything yet. Well, here, let's go to the ANOVA model. So right now, we're just doing the basic ANOVA model. So with the basic ANOVA model, we saw last week, the line 73, just calling the general linear model. So remember, everything we do in 513, as far as the linear model, we're going to see 2 procs that are the big ones we're going to use. Proc GLM for general linear model. So remember, regression lives within the general linear model. Analysis of variance lives in the generalized linear model. Analysis of covariance lives in the generalized linear model. And the other procedure we're going to use is proc mixed. And with chapter 16, we started talking about when effects are random effects. And that's where proc mix is really going to come into play at the end of 513 for handling these mixed and random effects models. we're also going to see ProcMix is going to help us out in chapter 18. We talk about model diagnostics, but we'll keep that on the shelf until we get to it later. Okay, so we got that. We got this, our basic model. Line 74 shows the categorical predictor, our factor variable, brand, and then the basic model. This option in blue, I'm telling SAS to print out the sums of squares type 3. Again, we see with the ANOVA model, with only one predictor, the factor variable, the overall ANOVA test, the type 1 sums of squares, and the type 3 sums of squares gives us exactly the same thing. So again, if we look here, this comes out of the SAS output. All right, so again, our 4 levels. So if we focus on the ANOVA table, remember the mean squares are quantifying the estimated variance between the cell means and the estimated variance within the cells. So we're within the levels. So we see the variance between the 4 cell means is over 5,000. No, it's 5,317.822. The average variance within a level, so the observations within a level, is only 6.13. So for us to see whether or not the variance between the cell means and the pooled variance within, whether or not they are, whether or not the variance between is statistically bigger than the pooled variance within, we create this F value, right? Which is the ratio of the 2 mean squares, 866.12. And this is the p-value. Remember, the F is really assessing whether or not those variances are equal. And again, if those variances are not equal, then that rejects the null of the equality of the cell means. So just like in chapter 16 with the Kenton data, for the Rust data, we have the same exact null assumptions, right? So in this case here, we have the same exact null. So based on that F, we have sufficient evidence in our data to reject the null in favor of the alternative. So based on the available data, we have sufficient evidence in our data to reject the equality of the on average Rust inhibitor rating across the 4 brands, where we have sufficient evidence to indicate at least one brand is statistically separating from the others. Note here, there's the F, and like we said, for the type 1, type 3 sums of squares, we get exactly the same thing. Here's the grand average mean. So, and when we start thinking about the factor effects model rather than cell mean model, remember that mu dot is being estimated by that grand mean at 60.25, which is basically just the average of all the data. This is our pooled standard deviation, which is nothing more than the square root of the mean squared error. And then look at the R squared, the percent of variance explained by the model. So knowing the brand level, we're explaining 98.6% of the variance in the Rust inhibitor ratings. Now, this is where you guys see textbook data and not real life data. The days I come across an R squared of 98.6 ain't that common. Ain't that common with real life data. But just keep that in mind. Again, the coefficient of variation ends up being the root MSE over the rating mean, the brand mean. Again, SAS is going to produce this little box and whisker plot. So visually, we could see, wow, brand 2 does appear to be statistically superior to the other 3 brands. And sort of like the Ken data said, it's like, okay, you got this winner, and then this second place one, brand 3, seems to be statistically superior to the other two. We haven't tested anything yet. We're just doing this eyeballing, just visualizing based on it. Again, there may be a couple graphs we want to create. So this is the code to create the means per cell. So I got the average rating per brand right there. And the one graph I really like, let's first take a look at this one. This one showing, really connecting the mean across the 4 brands. Now this looks like a shark fin, but nonetheless, when we're thinking about the null, how does this mean profile line look? Well, not line, this mean profile connected curve look. Now, for us to have not sufficient evidence to reject the null, so basically we have enough sufficient evidence to indicate the means are different from each other. The line, this figure should be a horizontal line or nearly horizontal. It's not. We see this big jump from brand 1 to brand 2. So looking at this mean profile line, I'm beginning to get some sense of going to reject that null, which obviously we already know the result. If I go to this one, this one's giving me the raw data. Give me the raw data per brand. Remember, when we're analyzing data, there's 3 things we need to know to analyze data. Those 3 things are the knowledge of the mean, which is this figure, knowledge of the variance, which is basically this figure here. But in reality, it's better to know all 3. So creating this overlay, which I think is the better figure. So again, the 3 things we need to know. Knowledge of the mean. It's this mean profile line showing that knowledge of the mean. Knowledge of the variability. This is showing the variability within each level. The mean cells are kind of getting a sense of the variability between the cell means. And then the third thing we need to know to analyze data is knowledge of the distribution. So 505, 506, you guys spend a long time talking about distributions. The general linear model, the underlying distribution is normality, which again, we're approximating with the T and using the F for some of the hypothesis testing as well, but we're thinking approximate normality. So in this case here, with this graph, eyeballing the data with this graph, this gives me, I get all 3 in one picture. So right away in this figure, I'm suspecting I'm going to reject that null, the equality of the 4 cell means. Additionally, I'm beginning to think I don't have enough evidence to reject the equality of the variances across the 4 levels. Because again, when I'm looking at the spread within each level, none of them really jump out. None of them really jump out more than the others. So to me, it's kind of like, okay, this, so before, so I would look at this spread before even analyzing the data. So right away, I'm getting a sense of, I'm going to reject the equality of the 4 means. I don't have enough evidence to reject the equality of the 4 variances. And remember, with the ANOVA model, one of the assumptions is homogeneity of the variance, which is the ANOVA model version of homoscedasticity of the errors that you saw in the regression model. So we got that right there. That plot we got right there on line 127 to 136, that is the best model to look at, the best graph to look at in conducting the ANOVA model. It gives you everything you need to know to have a suspicion of how the data is going to look. And it's a great visual for the investigator because he or she can see the data. You know, additionally, if you have one outlier, you know, the outlier would jump out here as well as one of the dots separating from the pack. Now, also remember, this differs from a regression model. You know, the regression model is assuming as the predictor goes up, a linear relationship. You know, with this shark fin, that's what we meant in chapter 16, saying the assumption of the relationship between the predictor and the outcome is not linear. This is an exact illustration of that lack of linearity. We're letting the cell means be whatever they are. Note as well, the p-hats from the model, the predicted values from the model are estimated by the cell means. And the residuals of the observations for the model, the EIJs, are the distance from the observed value to the predicted value. So for this circle here, the residual is positive because the observed values above the predicted. So again, remember the residual, observed minus predicted, alphabetically, O before P. This one here, its residual is negative. It's because its observed value is below the predicted value. We know the sum of the residuals within each level sum to zero. That's because we're dealing with the ANOVA model. Deviation sum to zero. We know the sum of all the residuals sum to zero as well. I mean, if each component is summing to zero, the sums of a bunch of zeros is still a zero. So we have that there. The book talks about a line plot. I'm going to show you guys how to do this in SAS G-plot instead of the SG plot. So in SAS G-plot, SG plot, the coding's a little bit more simplistic. The G plot has a lot of nice graphics, but the coding is a little bit more clunky, right? And this isn't really getting into teaching you guys SAS programming, but the idea is I'm leaving you guys templates that you can use for your own data if needed. So in this case here, when we look at this, let me look real quick. Oh, typo. And I called the variable average rate, not AVG rate. Real important. You guys just saw it there in SAS. And I'll fix it with the saving, is pay attention to the log. Right, the log is going to tell you something's wrong. Right, so one thing that you need to learn in the program is to keep track of what you're doing. And for me, I joke around with all the class. You know, SAS is your friend. Right? In this case, my friend SAS is saying to me, "Yo, knucklehead, you got a mistake in your code." And like we see in SAS, remember you got the 3 color codings: the red, the green, and the red, the green, and the blue. So remember, with SAS, the red, you're dead. Something's wrong in the code. Something's wrong in the code. The green is usually SAS asking you, what do you mean? Do you mean this? And then the blue's good for you. So I always think about those 3 phrases when I think about SAS coding and what the logs tell me. Red, you're dead, something's wrong. Green, SAS asking, what do you mean? It could be nothing, it could be a warning, it's a warning. And maybe something you don't need to worry about as well. When you see the blue, SAS is working for you. So in this case, I saw that mistake where I had the wrong variable name, but this creates this graph. And this graph here, now as you guys see here, is showing me the mean rating for the 4 brands. And that graph's fine, right? It's giving you a visual how the cell means separate from each other, But again, it's just the means. The three things we need to analyze data: knowledge of the mean, knowledge of the variance, knowledge of the distribution. This is giving us the means, but it's a good graphical layout, really stresses the difference between two. I think this one's a lot better. But again, the book talks to you about this line plot. This is a line plot. This is a line plot. As we start moving forward, the plot you use is up to you unless I specifically ask for a specific graph. I think this graph is the one I most commonly ask for when you guys are performing the ANOVA models. So some graphs may be something you use down the road that I may not ask for. But this one, the graphs we use need to embrace the things we need to analyze data. Variance is a huge component, right? Everything we need to analyze data forms a triangle. Knowledge of the mean, knowledge of the variance, knowledge of the distribution. This is not showing that knowledge of variance. And for the linear models, normality is the underlying distribution. But it's a plot. The book rates you to the scatter plot with the G plot that you guys see here. And this one doesn't have the mean. I think the one we did with SG plot works nicely. Then here's the template for the color plot in G plot. Yeah, it kind of looks similar to the SG plot. I think some of the labeling looks a little older. You know, if we start thinking about some of the cosmetics of it. And then this one is, now this one isn't too bad of a figure, but it's giving you this, you know, this kind of cylinder plot. But again, it's just only knowledge of the mean. Again, that's using Proc G chart. Again, another mistake by me. The variable is AV rate, not AVG rate. So when I go here, and our shark fin again, this horizontal line is the grand mean. Isn't too bad. Now this one, this plot I kind of like that I show you guys with this is G chart, right? So giving you guys kind of the, you know, kind of a little bit of a template of it. So we're going to get the axis label for the brand, the label for the Y variable, pattern yellow. I'm creating this horizontal bar chart as a function of the 4 brands. I'm showing the mean on the rating variable. And then I'm also given error bars and confidence limits at 95%. So take a look at this. So this one I think is pretty cool because it gives us a little bit of the summary and the mean rating and gives a graphical depiction. Now these are 95% confidence bounds. 95% confidence bounds that you guys see in the rating. So now when we start looking at this, it's kind of like, wow, right away we know we're going to reject that ANOVA because this one, even with the 95% confidence bound, doesn't overlap with any of the other confidence bounds. Now, one thing you'll notice, look at this one, look at this H, and look at this H. Basically looks like an H. They're not the same width. These confidence intervals you see here are basically the confidence intervals we saw with the proc means code. The proc means code, the confidence interval is based on the cell mean, the standard deviation for the cell, and the sample size for the cell. Right, so the 10 for each cell. So we got that there. Now remember, when confidence intervals don't overlap, they are statistically significantly different from each other. When confidence intervals overlap, that does not mean they are not statistically significantly different from each other. You may have a situation where confidence intervals overlap, but pairwise, they are statistically significantly different from each other. Well, I'm looking at brand 1 and brand 4. So if I follow this up, it looks like that upper bound is going to lie within the confidence interval for brand 1. Then similarly, if I use this lower bound, it looks like that lower bound lies within the confidence interval for brand 4. But the big thing you guys got to remember, it's not the confidence intervals overlapping. It's whether or not the mean for a respective cell lies in the confidence interval for the others, right? So it's whether or not the bar, the top of the bar, is in the confidence interval for the others that indicates whether or not the groups are statistically significantly different. When you're comparing the H's, right, the confidence intervals amongst each other, remember each confidence interval comes with error, right? So this H, I'm going to just take this guy out and bring it back, right? So if we go here, this H and that H overlap, right? But this confidence interval has a 5% error. This has a 5% error. So when you're comparing two, you're kind of creating a 10% error in the mix. So the pairwise comparisons is really whether or not the mean for each level is within the confidence intervals of the other, which indicates a statistically significant difference. But that's what we got right there. So now, one thing that we want to do is create the confidence intervals. And to create the confidence intervals so we did a bunch of graphics, but one of the things we like to do is actually formally ask for the confidence intervals. And so when we ask for the confidence intervals, we saw last week that or I guess last video we saw a little of the LS means option. Well, in this case, we're going to extend this a little bit more. And what I'm going to do here is we're going to do two things. Extending our code. First with the CL Parm, which is going to give me confidence intervals for the regression solutions, the parameter estimates of the ANOVA model, and estimate statements. Keep this in mind for where we're going next. Line 275 is going to give me the estimated means for the brand. Line 276 is going to use the mean statement to create confidence limits for the mean. And then line 277 does it with the LS means line. And if you guys see here, line 278, I'm using the ODS command. Remember with SAS, with the ODS, any portion of the output can be sent to a data file. And in this case here, I'm sending information from the LS means part of the output to this data set CL info. I'll show you guys this in a minute. Well, let's run the model really quick. When I run the model really quick, here it comes. Right, so here's the output. I'm going to go all the way to the top and work our way down. Right, we already know this. Right, so this is going to be the basic output. How's this output compared to this? I gotta go all the way up. Not trying to make you guys. How's that output compared to this? The one added benefit of the plot above to this plot is the plot above shows you all of the raw data. You know, this does give you a sense of the means. This does give you a sense of the spread, but I don't know where the raw data is here to get a sense of the spread. So that's why I like the above one better. So this is from the ANOVA model. This output you guys see here, this is being produced by the mean statement. So the mean statement on line 275. Then these are the means and the standard deviation. They're nothing more than the raw mean and the raw standard deviation. Another repeat of the plot. Now, if you notice with these two, we don't have the overall F in the upper right corner. This is from just the procglm command. From the means again, so this one's being produced by line 276. With line 276, right, line 276, this is giving me the T confidence interval for the ratings, right? So if you guys go here, you know, as we start eyeballing this, this is giving me the alpha level, no, the error degrees of freedom, you know, so again, our N total minus the number of levels. So 40 minus 4 is 36. This gives me the MSE, the critical T for the MSE, and the respective half width of the confidence interval. Keep in mind, this box you guys see here, that's being produced by line 276, the confidence limit of the mean, the CLM option. The one cool thing about this is it puts the means in order from the biggest mean to the smallest. The confidence interval you see here is the confidence interval we estimated with proc means. So if you go back to our data, if you guys remember, brand 2, we saw this with the proc means output. And we're seeing that with the SAS output. Similarly, mean 1, 41.55, 44.73. Right? You know, if you guys see that, you know, well, actually, let me correct that in this case here. Go back to the output. 87.85, 91.03. Brand 1, 41.55, 44.73. If we go here, it's not the same, right? So let's go ahead and write this down really quick. Let me move this over. The proc GLM. So brand 1 with the proc GLM, means command, I'll call it means line. The TCL mean. Now check this out. If we go back to the SAS output, so we got 87.85, 91.03, 87.85, 91.03. Go to brand 1. So brand 1, we got 41.55. And we go to 44.73. So if we go here, whoops, that width is 3.18 as well. 3.18 as well. So it's kind of, okay, we see this. We see this. And then even if you guys look here, let me go to the next one. Look at brand 3. Brand 3, if we look really quick, its estimated 95% confidence interval is 66.36, 69.54. Ends up being its 95% confidence interval. So again, we're 95% confidence interval, 95% confident that the true on average difference or on average rating is somewhere between 66.36 and 69.53 for brand 3. So if I go here, I just add this in, brand 3, so its estimated confidence interval, lower bound 66.36, upper bound 69.54, its width is also 3.18. So what you guys start seeing is the width of these confidence intervals are the same in the proc GLM output, not the same with the proc means output. What's the difference? What's the difference? The difference with the proc means is these confidence intervals, these confidence intervals with the proc means, so if we go here, the proc means confidence intervals uses the individual standard deviations. The proc GLM uses the pooled standard deviation, which again is nothing more than our root mean squared error. Is our root mean squared error. Which one's right? Well, let me word it this way. The difference between the proc means output and the proc GLM output shouldn't be really dramatic. If it is dramatic, then you got an issue with a violation of homogeneity of variance, right? And then that creates a problem because our model is not appropriate for the data in hand. So they should be pretty close. The ones we should use, the confidence intervals we should use are the ones where we have the most reliable estimate of the standard deviation per level. Now, I'm saying it that way, the standard deviation per level. The most reliable estimate of the standard deviation per level is our estimate based on the pooled standard deviation. Remember, we have no evidence of a violation of HOV. So if we have no evidence of a violation of HOV, we should use the pooled standard deviation. So our best estimate of what's going on should really be using these confidence intervals. Should really be using these confidence intervals. So again, it just happened to be that the raw standard deviation for level 2, matched the pooled standard deviation, right? Or the pooled variance. So the variance for level 2 was really close to 6.14, whereas the variance for the other levels was not. But the confidence intervals we should use are these. Now, if you go back to the graph, that I think is a really good graph, this one, you can see that these H's aren't the same. But again, when we're doing the graphs are for storytelling, not statistical comparison. So the fact that these aren't the same should not, they're there to tell the story. The statistics are going to use the correct model-based estimates. But again, this is a pretty good visual because it shows you the spread, the N, and the mean. Again, you know, so kind of give me a little bit of a sense, but of what's going on average. But I think you should be able to get some sense of what's going on with the storytelling there. So that's pretty cool. If we jump back to the output, did I close the output? I didn't mean to close the output. Let me just do it again. So this was our mean. These were our confidence intervals. When I do the LS means portion of the output being asked for in line 277 gives me the estimated means. Remember, this is giving me the pairwise comparisons. We have not done any adjustment for multiple comparisons yet. But what I can see here is, remember, this is level 1 compared to level 4. So based on the available data, we sufficient evidence that the on average rating between level 1 and level 4 are statistically significantly different. And again, if you go here, here are the confidence intervals between level 1 and level 4. You can see the confidence intervals overlap right there. But remember, significant difference. You know, if the confidence intervals do not overlap, you definitely have a statistically significant difference. When the confidence intervals overlap, it all depends on how closely they overlap. And to get that sense of closeness, it's whether or not this mean is inside this confidence interval that determines whether or not they're significantly different. And similarly, this mean within this confidence interval. And we'd see if they are not within those confidence intervals. So this group 1 to group 4 significant difference isn't, you know, is because the mean of one is not in the confidence interval for the other. The confidence intervals overlap, but they are, those two levels are significantly different from each other than all the other ones obviously are. The confidence intervals you get from LS means are exactly what we got from the mean statement. And then here, if you guys see here, the one cool thing with the LS means command is it's going to give me the estimated mean difference for the 4 levels, as well as the 95% confidence interval for the mean difference. So again, one thing we can see here is, okay, you know, so this is level 1 compared to level 2. So the mean for level 1 compared to level 2. So level 1 is 46.3 units on average below level 2. And we're 95% confident the true on average difference between level 1 and level 2 corresponds to level 1 being 48.55 to 44.05 units below level 2 with respect to average rating. Level 1 to level 3. And look at level 1, level 4. We're 95% confident the true on average difference between level 1 and level 2 corresponds to level 1 being somewhere between 0.42 units to 4.92 units higher with respect to on average rating compared to level 4, brand 4. This gives us this, you know, just showing you the means for the 4 cells. And then this block here, it gets really busy, especially when we move to two-way ANOVA, so you don't need to really worry too much about this one. Now, some of you guys may be saying is, like, well, what are you doing with this? And if you guys see here, I go to the listing. This is why I call it the data set. This one, I got the mean. I got the confidence interval for the 4 brands. Well, how do I know to use this command? And one of the things you guys saw in 5.11 rather, if you put this ODS trace on and you run your code, in the log, SAS is showing you what every portion of the output can be named as. All right, so again, I could take the, every portion of the output from the very beginning, the class level. I could send that to the data set with class level as the name of the data set. The number of observations, this portion of the output. The overall ANOVA, this portion of the output. The fit statistics, that's this portion of the output. The model ANOVA, the type 3 ANOVA, that portion of the output. The box plot to a figure. The other box plot to a figure. The means. The confidence level for the means information. So all this stuff can be sent to a data file. And what you guys saw I sent the LS mean CL information, which is this box right here, to a data set. And what I did here, is I sent this to the data set CL info. So I can use that for maybe printing or whatever. Here, the big thing is when you turn that trace on, it sends a lot of stuff to the output, to the log. And then you always just turn it off by rerunning the code. So that could be a little useful information if you want to send anything to the output. Let's jump back to the slides. So if we jump back to the slides, we just saw that. Now, one thing you guys will notice is with the ANOVA model, if the ends are the same, the confidence interval widths will all be the same, because the confidence interval widths depend on the best estimate of the standard deviation, the pooled standard deviation, the root MSE, and the cell size. Again, we saw some of the cosmetics all within the SAS graphs. Again, we highlighted the problem with the plots, or you need to know knowledge of the distribution, knowledge of the mean, knowledge of the variance. This is our formula for the confidence interval for the cell means, right? So it depends on our estimate of the sigma squared, estimated by the MSE, and the cell size. So for us, the T statistic we use, if the cell sizes are the same, that square of NI is going to be the same. S is estimated by the root MSE. The T is going to be from the T distribution. Now, the great thing with the GLM is the T distribution is not a function of the cell size, in this case, 10 per level. It's really a function of the whole ANOVA model, which the T's are distributed by the total N minus the number of levels, basically the degrees of freedom of the error. So again, sigma squared is estimated by the MSE. The T's have degrees of freedom N minus R. R, in this case, it's 36. We saw this with the, we just did the rust inhibitor one. Let's do it really quick for the Kent example. Now for the Kent example, if you guys see here, we'll come back to this one real quick, just in case I made any changes that I didn't retain. So let me jump real quick to the Kenton one, the Kenton confidence interval. Load the Kenton data set really quick again. I won't worry about, well, let me just show you guys this one really quick. This T lines, and then we'll go to this drop down real quick here in a minute. This T lines. So if you guys see here, I got the the basic ANOVA model. the T, then this is the T lines. So means covered by the same bar are not significantly different. So as you guys see, means not covered by the same bar. If you guys have letters here instead of colors, let me see if I can go to the listing really quick. Not showing it. So in this case here, this is showing the same color, right? So again, when these are by the same color or the same letter, then they are not significantly different from each other. But the blue, the red, no, they're significantly different from each other, and the green are. It's kind of a cool way to lay things out in a graphical sense. Show you this with the Kenton data set. So with the Kenton data set, here are our confidence intervals, right? So let's pay attention really quick to design one. So design one, we have this confidence interval, right? So we have a lower bound of 11.50 and 17.70, we round it off, right? So we go here, that's our confidence interval. So I'm going to jump back to Word really quick. So design one, we have the 11.50 to 17.70, which gives us a width of 6.2. Let's go to design two. So if we go to design two really quick, let's look at this as well. So you can see there we got 10.30 and we got 16.50 if we round it. So we go here and write this down. So design two, we got the 10.30, we got the 16.50, width equals 6.2. And then if we go to design three, I won't do all four, we'll just do these ones. So if we go to design three really quick, we could look at this. So this one is 16.04 as the upper bound, 22.96 as the lower, as the upper bound, 16.04 is the lower bound. So if we write this really quick, design four, we got the 16.04 is the lower bound, 22.96 is the upper bound, and then the width here is 6.92. So you notice these two have the same width, this one does not. Go back to our formula, right? So remember our formula is the T is going to have M-R degrees of freedom, so the T is the same. The S is estimated by the root MSE, the square root of NI. If you guys remember, the NI is the number of observations within that level. If you guys remember with the Kenton data set, the Kenton data set had the situation that the cell sizes were 5, 5, 4, 5. So design 1 and 2 have 5 as the cell size, the width's the same. Design 3 has a cell size of 4 because they had the one store that had the fire. So we lose that cell size as we start moving on. So that becomes that as we move on. And then we go here really quick. So if I jump back to this, so that's what we saw there. And then I do the same thing with the LS mean statement, as we can see. Now, show you guys something, right? If I put alpha equal 0.10 on line 61, this is going to create not 95% confidence intervals every time I ask a CL, it's going to create 90% confidence intervals. Then you see on line 65, I got alpha equal 0.01. The LS mean statement has the capacity, the capability, where you can specify a confidence interval in that level. You know, the LS means for that output alone. The proc line, this is going to create that confidence interval, in this case 90%, for everything in proc GLM, unless you specifically state a different value for alpha in the LS means line. So this is going to be kind of the big dog that's going to do it all, unless you specifically. If you don't have this here, then the LS means line will use this alpha. So if I look at this output really quick, you could see in the means line, it's 90% confidence intervals, but in the LS means line, it's 99% for the individual cells, as well as 99% for the pairwise differences. So just keep that in mind as we move forward with respect to that. And when we get here, we have that. And we saw this with the Ken data set. If you wanted to do, the exact level of whether or not a mean's equal to 19, well, we could do the confidence interval for that. All right, so again, we're dealing with the Ken data set, right? And we're doing with an alpha of 0.05. Well, we could look in this and go, okay, well, to test whether or not the mean's equal to 19 for a two-sided test, we could basically say, hey, is 19, if we're doing it for design 1, is 19 inside that confidence interval? The answer is no, then you have enough evidence to reject. If the answer is yes, for say level 3, then based on the available data, we do not have sufficient evidence to reject that null that the average sales for design 3 is equal to 19 in favor of the alternative does not equal 19. Suppose in this situation here, we wanted to do a one-sided test, whether or not the mean is, the null equal to 17.2 in favor of the alternative, the mean's truly greater than 17.2. Again, we could do a confidence interval as well. So in this case here, if I want to do this test with an alpha of 0.05, an alpha of 0.05, this is a one-sided test, a one-sided alternative. If I go here and go back to our subsequent code, where I said alpha equal to 0.10. Here comes the means output, alpha equal to 0.10, right? So in this case here, alpha equal to 0.10. So we want to say greater than 17.2, right? Greater than 17.2. We said it for design 2. We'll do it for both design 2 and design 4 and 3. Right, so greater than 95, greater than 17.2. Remember, if we're doing this with an alpha of 0.10, that means we need a one-sided confidence interval, right? So in 505, in 504, and in 506 as well, you talked about one-sided tests. I guess really 506. With a one-sided test, you could do a one-sided confidence interval. Remember, with one-sided confidence intervals, one of the bounds is going off to infinity or negative infinity, right? So you either have the upper bound going off to positive infinity or the lower bound going off to negative infinity, right? So in this case here, let me go ahead and take this portion of the, I'm going to go ahead and take this portion of the output. I go real quick here. So if I go really quick here and take this portion of the output, this really quick. So it takes all that to a RTF file. And then if I go here, here's my 90% confidence intervals. Let me take this. All right, close this out. So mu whatever greater than 17.2. Right, so that's just what we're dealing with real quick there. All right, let's take this just a little bigger and let's get this over here. So there's our alternative. So again, just put a question mark, which level we're dealing with. So to do this with an alpha, equal to 0.05, alpha equal to 0.05, we could do the one-sided test with a confidence interval. Now, in this case, one-sided, double the confidence interval. So we get a 90% confidence interval. But remember, a one-sided confidence interval. No, one-sided confidence interval has one of the bounds going to either infinity or negative infinity. The one that's going to either infinity or negative infinity, the one infinity we use is in the direction of the alternative. So for us, if I copy this and go, so for the one-sided test, so for this one-sided test, we want the infinity in the direction of the alternative. Right, so if we're trying to say greater than 17.2, right, greater than 17.2, we need the confidence interval, this one-sided confidence interval, not to contain 17.2 inside, right, not to contain 17.2 inside. So for this alternative, we reject this for design 4, right? Not design 3, not design 1, and not design 2. Because all those confidence intervals, 17.2 is inside those confidence intervals. So we can do that right there. So that's one of the benefits of the one-sided confidence intervals, being able to do that. We saw before, the difference of the means, we have the Ellis means doing all this for us. So again, with the Kent data set, we saw the pairwise comparisons last time. And now we start getting into the issue of how to do contrast within our analysis. And how to do contrast within our analysis, we'll start that in the next video, video 3. So again, we'll go here. These are our chapter 17 notes, right? So when we go here, you know, we're going to even dissect the contrast further in video 4. We'll dissect those even further. So, and we'll pick up with video 4 at the next time, which will be pretty cool. And go ahead and hit stop share, and we'll pick up with that the next time. So everybody have a good day, and I'll see you soon.